So we have to do work now. We can't talk about our crazy spam phone calls. All right. All right. So, what am I going to get for this first one? So, what do we get? Also, people of Zoom, if you ever want to be people of Classroom, like there's only 5 of us here today. So, there's definitely room for more of you. So, what are we going to do? What are we going to add to this? We're going to add water. We're going to put the OH on the most substituted carbon of our double bond. Here we go.
I was asked if you have to draw the hydrogen in the product.
No, because like since it's a what's it called? Since it's a skeletal structure, that hydrogen is just understood. So you don't need to show it. If it helps you by showing it, like when you draw your product, that's fine. But you don't need to show it because it's understood that it's there. So where does my bromine go? I can throw some more in there if it makes you better. Right? It goes to C, right? We're gonna make the carbocation. We can move a methyl group. And then we're going to add the bromine to that carbocation, that tertiary carbocation that we made after the rearrangement. And you're going to get that as your product. So I think we got right up to ring expansions. So I don't remember exactly where we were. It was a little bit further in the late section, but it's all right. So, right, so you go from a small ring to larger ring. Which reduces, oops, we'll make that letters, reduces uh, ring strain. Right, so when you do a ring expansion, the energy that you get is not only if you go from a secondary to a tertiary carbocation, it's also going from a small ring with a lot of ring strain to a larger ring that has less ring strain. So general rule is rings go, boy, people are just falling asleep in here. Rings go 3 to 4. So from 3-membered rings, they can expand to 4-membered rings. They can go 4 to 5, or they can go 5 to 6. So we don't expand 6-membered rings because we've set 6-membered rings to have 0 strain, right? So there's no driving force for that 6-membered ring to try to get bigger because it's already the most stable ring that we can make. So we go 3 to 4, 4 to 5, or 5 to 6. 6, we stop, we don't expand anymore. So what you're looking for a ring expansion is you want to have a double bond beside or adjacent to your ring. so that when you do your mechanism, right, you put a carbocation beside your ring. All right, so you always have to do a ring expansion, that carbocation has to be right beside the ring. It can't be like any further over, it has to be right beside it. Now, what I like to do is I like to number all of the carbons of the ring. This is going to help you track where groups are from, where groups need to be from your starting material to your product, right? So we're going to go 1, 2, 3, 4, and the carbon that has the carbocation, that's going to be 5. So it's going to be the carbon that has your carbocation is going to be the number of the ring you're going to, right? So I'm going from a 4 to a 5, make the carbocation 5. So now what happens here is in a ring expansion, we're going to take the electrons between carbon 1 and carbon 4. We're going to break that bond. And those electrons are going to slide out to carbon 5. So you're going to break the bond between carbon 1 and carbon 4 and make a bond between carbon 4 and carbon 5.
The question was, is the carbocation always number 5? So it kind of comes down to what number you give the carbocation.
No, you number the cation as the number of the ring you're going to. So I'm starting with the 4-membered ring, so the cation becomes 5. If I had a 3-membered ring, the cation would be number 4 because I'd be going from a 3-membered ring to a 4-membered ring. I do it that way because I just think it's easier to keep track of, and like I just do it consistently the same way, so you can always kind of follow along. So I just number all of the carbons of the ring, and then I make the carbocation the number of the ring that I'm going to. So I'm going from 4 to 5, so I make the carbocation 5. So I'm now going to break the bond between carbon 1 and carbon 4, and I'm going to make a bond between carbon 4 and carbon 5. Let me get rid of that real quick. So now I've got 1, 2, 3, 4. That's a really ugly 5, but 5. So what these numbers do is they're going to help us know what should be on our what group should be on what carbons of our product now. So carbon 1 in the starting material had an ethyl group on it, right? Nothing happened to that ethyl group. That ethyl group should still be there. So this ethyl group right here is this ethyl group right here, right? Carbon 1 had an ethyl group in the starting material. Carbon 1 needs to have an ethyl group in the product. Carbon 5 had a methyl group on it, right? This methyl group right here. Nothing happened to that methyl group. Carbon 5 in my product needs to have a methyl group. So that's that methyl group right there, right? So if there's more groups, there are more carbons or groups on your ring and it does an expansion by numbering the groups, by numbering the carbons, you will know what group, what substituent needs to be on what carbon of your product. All right, so electrons left carbon 1, right? So we had the electrons between carbon 1 and carbon 4, they left carbon 1, right? That means carbon 1 ends up with a positive charge because electrons left it. So carbon 1 gets a positive charge. And now that's what I'm going to add my Br minus to. That's the carbocation I'm going to have my Br minus react with. Right, so then Br minus adds to this guy.
I was asked why carbon 1 ends up having a carbocation.
So right here, these, make them green, these 2 electrons, right, become the electrons between carbon 5 and carbon 4. So the electrons left carbon 1. So since electrons left carbon 1 gets a positive charge. Nine ten, first person left. Like, I'm out. The first person left Zoom at 9:10. They're like, I'm out. Drop days tomorrow, plenty of time.
I was asked to do an example where carbon 5 had 2 methyl groups on it, and that's what I go ahead and draw right after this.
I can draw it better than I can. So you're saying, let's say I had this, and then I had like that. There. Yeah, so if I had that, right, and I use like HBr, I would end up getting this as my carbocation. Good, here, let me draw out more stuff so I'm not just like losing everyone, right? So I get to here, and this is an important example to talk about in that, right, I am trading tertiary carbocation for a tertiary carbocation. Right? So both carbocations are tertiary. I don't gain anything energetically from my carbocation when I do this ring expansion, right? I'm trading a tertiary carbocation for a tertiary carbocation. That's a wash. Where I'm getting my energy, where the molecule's getting paid off for doing this rearrangement, is I go from a 4-membered ring that has a lot of strain, right? Bond angles are 90 degrees, really far from 109.5, to a 5-membered ring whose bond angles are like 108 degrees, which is a lot closer to 109.5. So there's significantly less strain in the ring. So even though my carbocation is the same, my ring gets better. So I get energy, I get more stable from doing this ring expansion because I'm making a more stable ring. So the carbocation is neutral, ring is better. Then I'll add bromine to this guy. Great, so my product is going to be, we'll go through all the steps. Make this carbocation. 1, 2, 3. Oops, do it the other way. We'll do it the other way. 1, 2, 3, 4. It doesn't matter. Right. The numbers are just there to help you keep track of stuff, but I'm trying to be consistent, so I'm going to break the bond between 1 and 3 and make a bond between 3 and 4. So I'm going to be making the bond from the carbon to the carbon that makes the bigger ring size. So just trying to stay consistent with what I did the last time. But if you numbered them like A, B, C, D, it doesn't matter. Like as long as you're like, as long as you can track what's where, that's all it's there for.
So in this case, you have to break the bond. You have to add the bond between 1 and 4, between 1 and 3.
You have to,
you can't add it between.
so you have to take these and come over. Does that make sense? Right? So you can't like move the bond between 2 and 3. It's too far away. It has to be the bond right beside the carbocation is the one that has to move. Yeah, like I often will like we'll do this on like you're just taking the electrons and they just go and they just pop out. They just pop out one carbon. It's all that's happening. You're just trying to find the bond that you can just kind of push the electrons over and make a new bond. All right, and so now you're gonna get now here's where we can get a little tricky. Carbon 4 had a methyl group on it, right? Because carbon 4 had this methyl group right here, so that needs to be this methyl group. Carbon 1 had electrons leave it, so it has a positive charge. What kind of carbocation is that? Can I move something from another carbon to make it a more stable carbocation? I can't move the methyl, but carbon 4 is a tertiary carbon, right? That has a hydrogen on it. So now I can move that hydrogen. I can do a 1,2 hydride shift. And now that makes a tertiary carbocation. Now that is the best of this carbocation I can make. So, so I've got this tertiary carbon right here, can give up a hydrogen. If I tried to move the methyl from carbon 4, I would just end up making another secondary carbocation, right? I wouldn't get anywhere. Do you see that? Right, so if you move this methyl group.
I was explaining why you can't move the methyl group.
Yeah, if it was a quaternary carbon, then you would move the methyl group. But because it's a tertiary carbon, you can only move a hydrogen. Because moving one of the carbon groups just gets it back to being a secondary carbocation. Now I can add my ethanol to this carbocation, and that would get us to that. I added ethyl. I added ethoxy. Right, so, right, I add my...
I was asked if the carbon bonds to the carbocation.
No. So when you add the alcohols, right, the thing that you're having it react with is it reacts with the lone pair on the oxygen. So that's what makes the bond, is the lone pair on the oxygen attacks and gets you here with a positive charge, and then you have another ethyl come by and take off a proton to get you to the longest arrow ever. There you go. To give you your product. So right, whenever you make a secondary carbocation, again, doesn't matter how you got there, you need to take a second and go, hey, can I move this? Can I do another rearrangement? Can I make it more stable? Right, so I went secondary to secondary, right? And I got paid off by making the molecule have less ring strain. Right, then it was like, oh, I can do another rearrangement and go from secondary to tertiary and become even more stable. Now that's what's going to react with my alcohol. I can go back, sure.
That structure down there is basically the same one as up there, but you just added a hydrogen in.
What was that question again? I'm sorry. You said that, so, yes, from here.
I was asked why the rearrangement actually happens, and the addition doesn't happen first.
It could have reacted with this with the carbocation here. So the alcohol could have added here. But for the most part, reactions that happen within one molecule are faster than reactions that happen between two molecules. So that hydride will move from carbon 4 to carbon 1 faster than the ethanol will find this carbocation to react with. Does that make sense? Right, so I use this example later on, right? But when you clap your hands, it's really easy to do, right? Right? But then you've never missed clapping your hands, right? But if you high five someone, you can get the awkward high five and miss, right? Because then that's two people having to come together to make a reaction, to make a clap, right? So if you're doing a reaction with yourself, very easy. But then this, I would go high five someone, but you're all diseased. So Trump got a COVID test too. Then how he ended up in the hospital. I'm just saying. So you can just think of it as it's harder to bring two different molecules together. That's slower than having the molecule react within itself. So that hydrogen moves faster than the ethanol has a chance to add.
So I was asked where like the extra proton comes from after you add the ethanol, and then with that, where the second ethanol comes from.
Yeah, so when you add water or an alcohol to a carbocation, you add it, and that proton, this proton here, is still on the oxygen, right? And that's right here, and you have to show the step that removes that proton from the oxygen, which is another molecule of ethanol coming in and adding, right? Because I have like shortcut the mechanism because I've shown you the mechanism before, right? But remember, you have to protonate the thing that reacts with your double bond is protonated alcohol. So the last step before you make your product, so this step here, right? This step here is turning this alcohol back into the thing that needs to react with the double bond. Why are you confused? So we draw our mechanisms, and I know that when you look at them, you're thinking I've got one molecule of cyclopropane, one molecule of ethanol, and one molecule of sulfuric acid, right? That's how you're reading it. But you have to remember that reactions happen in like bulk. So there are billions of molecules of ethanol. So I need the next ethanol that's going to react to come grab a proton to finish off one reaction and start the next. So I know we draw, so like it's not just that you have one molecule, and one molecule all reacting, right? You have one molecule, you have billions of this molecule, billions of this molecule, and billions of the other one. And they can kind of cross what reactions are happening. So like in the flask, if you're doing this reaction, you've got millions of reactions, millions of this happening all at the same time, all on different spots of the reaction mechanism. So this is, sorry, I can't do that. This is just an extra, it's the ethanol that I need to do the next cycle through the reaction. If I don't put my carbocation right beside the ring, I can't do a ring expansion. So here, right, where am I going to put my carbocation? B, right? It's going to go on the most substituted carbon. So this carbocation is too far away from the ring to do a ring expansion, so you don't have to worry about it, right? That carbocation to do a ring expansion has to be right beside the ring. So if it's not right beside the ring, you don't have to worry about a ring expansion. It's just going to react like it normally would. So far, so good? So these are the only two reactions, adding HX or doing a hydration, that go through a carbocation mechanism. So these are the only two reactions that you need to worry about carbocation rearrangements for. Right? So we have a bunch of, our next few reactions all share the same mechanism and don't ever generate a carbocation, so you never have to worry about doing a carbocation rearrangement. So our first thing is going to be a halogenation. So halogenations, you add X2, either Br2 or Cl2, across a double bond.
So I was asked why it's only bromine and chlorine and not other halogens.
Because fluorine never reacts. Like fluorine doesn't do anything productive. And then iodide is not reactive enough. So like fluorine's not reactive enough. Iodide is not really reactive enough. So it's only bromine and chlorine that work. And the product is called a vicinal. Make sure I spell this right, which I did not. So it's a vicinal dihalide. And vicinal just is a fancy way of saying side by side. They're on adjacent carbons. So you have your double bond. You add your halogen. And you put your halogens on opposite sides. So, because of the mechanism, which we're going to show in a second, the products, the halides, so the actual product is you're going to have one bromine that is up and one bromine that is back. So they're going to add anti to one another. They're always going to add on opposite sides. Now you don't know, this is relative stereochemistry. You don't know which one's the wedge and which one's the dash. All you know is they're always on opposite sides. So vicinal. So these are vicinal. Oops. Let me actually make it right. These are vicinal because they're on adjacent carbons. Vicinal means, vicinal dihalide means the two halides are on adjacent carbons. That's what vicinal means. So vicinal diol is two alcohols on adjacent carbons. Doesn't matter if they're wedge or dash. Vicinal is just, it's 2,3 or 3,4. Anti being an anti-addition means that they're on opposite sides. So anti-addition means they're put on opposite sides. Syn addition, which we'll get to later, means they're put on the same side. Right? Makes it look like an I and not an L. Right? They're on opposite sides. If you looked at it quickly, it might have said opposite slides, and I think that's very confusing. All right. So the mechanism tells us that explains why these are always on opposite sides. So let's go to our double bond. And we've got our halogen. Now, if you look at a halogen, you would think, okay, they're both the same atom. They're not going to have an unequal sharing of electrons, right? The one's not going to be positive, one's not going to be negative. But halides have really big electron clouds. and they're polarizable, read squishy. So you got these big squishy electron clouds, and they kind of wobble back and forth. So you can get points where there are more electrons that have kind of sloshed to the side of one halogen, and then they'll slosh back to the other halogen, right? So overall, right, on average, there's not one that's positive and one that's negative. But you can find instances where the electrons have gone to one halogen more than the other. And in these instances, you can end up with points where you have a partial positive halogen and a partial negative one, right? Where all of your electrons have kind of, that is the right-hand side, where all of your electrons have kind of sloshed towards the right-hand bromine and made the left-hand one just a little positive. I think they're talking about Jello shots. I'm confused. Help me, Zoom. Big, no, like the big Jello like casserole things that are like, and you just like. Blah. Someone's been watching too much The Great British Bake Off. Guilty. It is such a good show. What's great is, on a side note, right? If it was an American show, like halfway through, like someone would like knife someone for like $10,000. Like I was watching one that someone, their chocolate, when they were like doing the technical challenge, like solidified, and the person behind them was, here, take my chocolate so you can finish. And I was like, you guys are so nice and like European and you're so Britishy. This is so cool. And American had been like, ha, your chocolate froze. I'm gonna win money. Woo! And like would have stepped over their dead body. So like I was just like, and like, you know what their prize is? They get a plate. At the end of 10 weeks, they get a plate that says winner of the Great British Bake Off. That is all. That is all. Anyway, get on Netflix, watch the Great British Bake Off. Noel is the best host. Noel is the best. Noel and Sandy, that's my team. All right. So we're gonna do the same kind of thing that we did with our hydrogen and our bromine. Our double bond is gonna add to the positively charged halogen and push electrons over. But what happens here is one of your lone pairs from your bromine that you're adding to kind of simultaneously adds back to the double bond. So as your double bond in the transition state, right, you're starting to make one of the carbons slightly positive, right? It's starting to become positive. Electrons are starting to leave it. As it starts to get positive, the bromine that you're adding to goes like, I got you, and gives it some electrons, so it never makes a carbocation. So instead of the carbon ever being positive, like full on positive, you end up with a positively charged bromine. Now I'm going to put this like out towards us. Right? Plus I make Br minus. This is a bromonium ion. If it's a chlorine, it's a chloronium ion. Right? So now, instead of your carbon ever being positive, your bromine is what ends up being positive. So I never have a carbocation, so I could never do a carbocation rearrangement. Right? So you don't have to worry about that anymore. Now, I've got to add my bromine, my Br minus, to this. Bromine is really big, right? So you've got this bromine, the way I have it drawn right now, is pointing out at you. It's blocking the top side of the molecule, right? You've got this great big bromine, like being a bouncer, right? Nothing can get in from that front side. So the Br minus that adds has to add from behind that positively charged bromine that you have on top, right? So that means it came from behind. So this bromine stays forward. The bromine that added came from behind, so it ends up back on the back side. So they're always on opposite sides because when the first bromine adds, it blocks one of the two faces of the molecule, and the only way to add the next atom is to add it from the opposite side, to add it from the open face that's not blocked anymore. And that's the whole mechanism. It's just free money, right? Now, there's not a whole lot in the terms of like examples I can do for this because it's always the same thing. Right? You're going to add a chlorine to each carbon of the double bond, and those chlorines have to be on opposite sides. Here, it doesn't matter which one's up and which one's down because, so here, right, I'm going to put one bromine forward, one bromine back, right? So if on this carbon here, right, I've got this methyl group is in plane, this kind of ethyl group is in plane, bromine's forward, that means the other ethyl group has to be back, right? You always have two groups in plane, a wedge and a dash. And if I say, hey, that bromine's the wedge, that means the other group that I have to add has to be the dash. That good? But there's not a whole lot of ways to like dress this up because it's always one side, other side, wedge dash. Right? We have halohydrons. So the halohydron synthesis, you add X to one side and OH to the other. Oops. So you take X and then you add water. And then that lets you add X to one side and water to the other.
I was asked what happens to the other halide.
He just becomes acid. I'll show you. Yeah. He gets washed down the drain. He goes out to sea. It's like a Nemo situation. All right. So this product right here, when you have a double bond and when you have a halide in an alcohol, this is a halohydrin. So halide plus alcohol is a halohydrin. So, great. And again, it doesn't matter which one you make the wedge and which one you make the dash. It's going to be the same thing. So this versus this. We don't know what enantiomer we make, but we know what diastereomer we make, right? So we know that they're on opposite sides, but we don't know which one's the wedge, which one's the dash. So we know the relative stereochemistry, but not the absolute stereochemistry. So the mechanism for this is pretty much the same as the mechanism for a halogenation, right? So we're going to have, yes. Okay, so the beginning is exactly the same as what we did before. To add our double bond to one bromine, kick electrons off. And we're going to have the lone pair from our bromide add back to the carbon that's becoming positive of the double bond. I'm going to make a rhomonium ion. Cool, cool. Now, we make Br minus. Reactions are a race. And so we've got Br minus, and we have water. Water is a better nucleophile than Br minus. So water is more apt to add to something that is positively charged than Br minus is. So before Br minus has a chance to add to the rhomonium ion, water will add and push electrons up onto the bromine. And this is very similar to when with H3O plus, how we added to the atom, we grabbed the hydrogen and pushed electrons onto the oxygen. Bromine's positive, but it's positive because it's making too many bonds. We can't add to the bromine because it doesn't want to make 3 bonds. It just wants to get its electrons back and go back to making 1 bond and being neutral. That's why we don't add directly to the positive atom. We add the one beside it. Right. So then this is going to, same thing, the bromine blocked the top face. And we end up adding water. We're 1 hydrogen away from giving us the product that we want. And we have a lot of water. Right, so another molecule of water can come in, grab an extra proton, make the product and generate H3O plus. So the Br minus hangs out with the H3O plus to make a salt, basically. That's where the Br minus ends up. So this got a little bit longer. Just wait. But what I want you to see, one thing that will make your life easier as we go through stuff is don't look at all of the mechanisms as these unique things that don't share steps, right? First step right here, that's from the halogenation, right? So if you know the halogenation mechanism, you know how bromine or chlorine adds to a double bond, right? So you know how to get to the bromonium ion, right? So that's the halogenation. So that's not new for this mechanism. This last step right here, called 2, where we have an alcohol that has an extra proton on it that we have to pull off with water. That's the last step of a hydration, right? Right? So you've seen that before. The new thing is kind of how the water adds, right? The water adds to the rhomonium ion. That's new. But in a lot of our mechanisms, we can start looking at things and going like, oh, this is a step I already know. This here is a step I already know. I've just got to have this new step that I can use to like stitch those two things that I already know together as opposed to looking at each and every mechanism as this like standalone thing that you've never seen before. You want to look at each of them and see where the commonality is so you can start stealing steps from other reactions, as opposed to being like, all right, I have to memorize hydrohalogenation. And now hydration, I'm going to treat like it's a totally different thing, even though they both make carbocations and add something to a carbocation. But I'm going to treat these as different because I want to make my life harder. Then halogenation, I'm going to treat halogenation as something completely and totally different from halohydrin synthesis, right? I think you want to try to do your very best to like pick out steps in common intermediates and go like, oh, I know how that reacts. So once I get to this thing, I know what I have to do with this, right? So once you get to this, right, you should go like, oh, I know what I have to do because in hydration, I have another water molecule come in and grab a proton, right? So once you get to this structure, you don't have to, it's not like it's a unique thing anymore. You're like, oh, whenever I see this, a water molecule comes in and grabs a proton. Yes, sir.
I was asked if we have to show the bromine, the Br minus, making a bond to the H3O plus somehow.
No, like they would just hang out close together. Like, so you're not gonna like bring them. You're not gonna like draw an arrow, right? You're gonna have H3O plus with Br minus just chilling out beside it. You don't have to like show that they come together. One thing that organic chemists are really, really bad about is we have a tendency to drop counter ions all the time, right? So like things that like when we have metals, like a metal that's positively charged hanging out by a negative charge, we have a tendency to, unless we need that metal goes away, and we just have the O minus or the C minus doing its thing. So it's there, right? But for this mechanism, you don't have to keep drawing it over and over again. So remember when you had like spectator ions in like Gen Chem, when you would like you could cancel them out and to get down to like the core reaction, right? You generate the Br minus. Cool. You know that exists. But that Br minus is just hanging out, not doing anything here. And then it's just hanging out, not doing anything here. So you don't need to draw it over and over and over again to be like, yeah, it's still there. We're good. So, yeah, so do your very best to like try to like pull from previous reaction mechanisms as opposed to just like treating all your reaction mechanisms as these unique things. I think we will call that here.